Recording in progress.
Okay. Now I think it's working. Also online, I think you can see us. Okay. Okay. So let's continue with the second part. Now we are going to do supervised learning 2. Okay. So yesterday we were doing supervised learning 1 at the same time. So let's do a small again recall. This should be lecture 4. Okay, just to learn the topic. Okay. I don't know. You see it with a better resolution than here, or less? Here I don't see it with a very good resolution. Do you see it in the screens with a good resolution or not? It's fine. It's fine. Okay. It's just maybe this here that we don't see it. Okay, it's okay. Okay. So supervised learning. Yesterday, remember, we were saying that we had 2 kinds of data, features and outputs, and we had some examples, and we call features X and we call outputs Y. Okay, and then we have shown the linear regression example. We remember this X is all the data matrix. Sometimes we do just the linear combination of the data, and sometimes we add other polynomials. Again, I say it again, this completely arbitrarily. Why polynomials? Okay, why? But let's start with something. In finite elements, we do also polynomials. The difference is, and maybe it can help this, the difference is that in finite elements, we use polynomials, but we use local in the domain. We have a physical problem. We have compact support here. The polynomials are in all the domain of the data. But you can do the same thing also with bases that are, in some places are polynomials and the other are 0. You could also extend it. Or use other kind of bases, okay, like wavelets, for example. Yesterday we have seen it's already there. Yesterday we have seen the Tikhonov regularization. So why is helpful the regularization? Today we have seen many other ways of regularizing. We have seen the interior point method, how we regularize. We have seen how the augmented Lagrangian we regularize. So regularization in numerics, in mechanics, when we solve problems, it comes with many ways, and different ways. And also in machine learning, as we have seen yesterday, we can see it as just making positive definite matrix, okay? But you cannot do it too much, because if not, you are going to underfit. But if you are doing it too slow, you are going to overfit if X is too large. So this has no inverse. Okay. Remember that we were speaking about L1 regularization, which is a sparse solution of the problem. So it's the best way to approximate the problem of a real L0 optimization problem. It was another regularization. Sometimes you want to have a sparse representation of your data or a sparse representation of your solution. Today we have seen Laplacians also. In Stokes, we have seen this in the cost. Here we see this smoothing. We have seen also the variational form. We have seen also the total variation, which is very used in, yes, it's used in image processing. Okay. So yes, so another way of regularizing was saying, okay, what I want, it's not to regularize the L2 norm, more or less in average of the gradient. I want that the gradient, maybe there are places where they are big and places where they are not big. So and a lot of places where it's going to be 0. So that the gradient of theta, I want that is going to be sparse. So the new solution will have a lot of gradient equal to 0, very small gradients here, and some places large. So almost 0 here, almost 0 here, almost 0 here, and just some of them very large. If you do L2 normal regularization, you will have something in between. You lose information. So typically, these kind of things, we call it priors. Okay? Priors because we have more information about data than what you are supposed to propose. And regularization comes as a prior information of the data. Okay? And then, after the linear regression and polynomial regression, we move to logistic regression. The first example we've seen was to classify data, tumor size, malignant or benignant. But the difference, the big difference, is y equal to 0 or 1. Okay, this was this case, 1 class or 0 or 1. Today we will see multi-classification. So the example 2 with 2 dimensions was the tumor size and the age, and we wanted to pass a straight line. And we have data here, and we have data here. Again, in this case, if you want a line, horizontal line, or a straight line, you will do linear hypothesis function. Important, and I say it again, x of theta is linear in theta, but it's not linear in x. So maybe here it's linear also in x, but maybe x can be quadratic, like here. Okay, so just to remember that theta is linear, but not in x. But then this linearity that we have in the hypothesis functions with theta, we lose it because we pass this Heaviside function, which is discontinuous and clearly non-linear. And even if it's continuous and differentiable, it's not linear. So if we do a smooth version of the Heaviside function, which is the logistic function, or the sigmoid function, very famous sigmoid function, we have differentiability, we have continuity, but it's non-linear. Okay, so we cannot use anymore solving linear system of equations as we do in least square problems. We need to use gradient methods, or steepest descent, or stochastic gradient. Why? Because we have now non-linearity. Classification, we have non-linearity classification. We have understood the importance of P, or how we can interpret this solution in terms of probabilities. We can say if it's a grade 80% of you are more sure that you are in one side than in the other one. Okay. This boundary, we call it decision boundary. I plotted here just one straight line, but we can have more parabolic lines. And finally, a very important part of the talk was about the negative log likelihood of cross entropy. Tomorrow morning we will see and understand why it's called negative log likelihood, and we will try to see a statistical view of this problem. Okay. So what was the cost function? The cost function was 1 minus y minus the log and y minus the log. And as I was saying, and as we were doing with interior point methods, we penalized a lot when y should be equal to 0, when g is equal to 1. So if y is going to be 0, we want to predict to be 0 and not to be 1. So if we predict to be 1, it's going to be 0, and then this is going to be infinity, minus infinity times minus infinity is infinity. So you penalize a lot to go to the other value that you can go. This is the intuition of the non-negative log likelihood. Okay. So this function here, and we had some properties, and we exploit these properties, and we will see today how we exploit it also. The property was that the derivative is a function minus 1 minus the function. Okay. Okay. So we compute the gradient, and we have seen that the gradient has some advantages with taking this function. Why? Because 1 minus g, you have g minus 1 minus g, which is the chain rule. So this derivative, you cancel one with the other, and then these numbers typically goes to 0 because 1 minus 1 or 0. You will not have it anymore because it cancels this with this, and probably it's going to be more stable numerically. And also, you see that we can simplify it, this with this, and we can take factor, and then we end with this formula here, which is very simple formula, and recalls us or reminds us to the least square problem gradient. So it's the gradient is the same as the least square problem, but just instead of having x of theta, we have g of x of theta. So we pass the sigmoid function to here. Probably this is why it's called logistic regression, right? But see that the gradient is very expensive, very cheap, because, and I don't know if we did it in the practice, but f, you have to compute 1g. So once you compute g, you have already it for the gradient. So you need it for the cost, but you also need it for the gradient. So you can compute it just once, and then you compute the cost and the gradient. Okay. Remarks. We were saying that we can take gradient methods because we don't want to do inverses, and we are going to use line search, theta, tau, or learning rate in the world of machine learning. And we were saying that instead of gradient, we should take a stochastic gradient because even computing this is very expensive. All the sum, all the data, 1 billion computation of this. It's too much. So you take just at each iteration, you take hundreds, 100, and an iteration. And when you have all the data computed, then you call it epoch. Of course, you need also to use regularization. Okay, so another thing I forgot to tell, and also Tony was explaining yesterday, when we are using with large data, yesterday was not very large data, but when you're using large data, gradients is expensive. So imagine how we have to change our way of thinking in machine learning in comparison of what we do in computational mechanics. Now we're going to be very fast, a lot of data. We have to forget about doing it very precise and Newton and just few iterations. Fast. A lot of data and just a summation of vectors. Maybe matrix vector multiplication at most, but not inverses. Okay. So even the gradient, which is matrix vector multiplication, is already super expensive if you have 1 billion data. And one step of gradient, and you have to do thousands or hundreds of steps, it's already very expensive. So what do you do? What you do is just take just partial gradient. But in fact, computing the cost is also very expensive because, as I was saying, you have to compute all the G's. So it's difficult, two things, and this I forgot to say it, but I will say it today. gradient expensive. Then the stopping criteria for unconstrained optimization lecture 1. The stopping criteria, the norm of the gradient is smaller than this than eta. This when we do optimization, we do this in unconstrained optimization. So the stopping criteria is also expensive. And the cost is also expensive, computing the cost. Okay, so what do we do? Instead of doing gradient methods, we do stochastic. Instead of using the stopping criteria of the gradient of G of F, what do we do? What other? We have to take a stopping criteria that is not expensive. So one example would be number of iterations. Okay. Sometimes if the problem is convex, you can, as I was saying, how far you are from the dual, and then you can see how if you have the values, you can know which is the lower bound. Okay. And computing the cost is also expensive. What do we do? Sometimes we don't compute it. But someone can say, okay, if the cost is expensive, and we have seen it yesterday, then what do we do with the line search? Remember what I explained for the line search? Exact line search. Or backtracking. Remember? Lecture 1, I think. Line search or learning rate is the same. We have two possibilities, or exact or backtracking. Exact, we were saying, usually used when computing the cost is much cheaper than the computing the gradient. But here the cost is expensive and also the gradient. We cannot do an exact line search. Or we can do an inexact, which is backtracking. What does it mean? You start with a value, and then you divide it by 2, by 2, by 2. And when you have the cost that has descent a little, then you say this line search is good. So you start with a large value. If the new cost is larger than the one that you had before, then you divide it by 2 because you have a descent direction. You know that you have a descent direction. You divide it by 2. Is it descending? No. You divide it by 2. Is it descending? No. And up. And when it's smaller than the cost function you had, then you take this line search. But here we have a problem. Computing at each, you start with tau equal to 0.1. You compute the cost. But computing the cost and say no, the cost has increased. It's very expensive. So you don't want to do this backtracking. You don't want to be sure that the next step you have descended your cost. So you cannot do backtracking. So you cannot guarantee that you are going to descend for 2 reasons. Because you are not doing line search with backtracking, and the second thing because you have a stochastic gradient. So what people do typically, if you don't want to see the cost, you just imagine you are in a mountain and you want to descend. If you don't want to see if you were now in the next step higher or lower than the point that you were, you don't want to look up. You just say, okay, I'm not going to do this, but I will stay all the time, look locally and take very small steps, very small, many steps, but very small. I will always know that I will descend. very slowly, but I will descend. But I will never look up and compare with my neighbors to see if I am better or not than before. So you just go down with a very small steps. You can do this. Okay. So you take tau very small. Problem of tau small. If you take tau always very, very small, but fixed, the same one, then you will converge, but you will need a lot of iterations. Okay. So what is happening? Yesterday we've seen it. We took different taus. Okay. And with different taus, if you took a fixed tau, but large, at the beginning you were descending, but at the end you were increasing. It was not the right tau. At the beginning, the right tau was this one, but then at the end was another tau, smaller. You didn't adapt your tau, your learning rate. Okay. So typically, what you do is maybe you can take it very small, okay, but you will not know that you will descend always. And even with stochastic gradients, sometimes it happens. And I think if some of you have seen minimization problems with stochastic gradients, you have seen that maybe you are doing like this, and there are some very noisy convergence lines or curves. There are theory on that, and there are theory that proves that you will descend in average at the end. But you cannot have a very monotonic descending curve like this because you're using a stochastic gradient. Okay, so this is the problem of machine learning with optimization. Gradient expensive, you use stochastic. Stopping criteria expensive, maybe you use numeric iterations. And the cost is expensive, so you take a very small tau, always to know that you will converge. Which value was yesterday, more or less, the tau we took at the end?
0.1, maybe.
Yeah, yesterday we took, I think, in the practice part 0.01. I think if you took 0.5 was or 0.5 was too large. Okay. Remember the line search, just to say, for the augmented Lagrangian was the penalty term for the dual. Okay. Let's continue. So yesterday we were doing this, and we have been doing it for classification, but just classification of being 1 or 0. Now what we want to do is to do multi-classification.
I have a question. So yesterday we saw that even we can still minimize the problem, but the cost function will rise. Is this why is this happening?
Yes. So yesterday, maybe some of you, if you took large tau, happens something like this.
Yes.
For example,
yes.
Or maybe even like this.
Yes.
So, but you take the same tau always. Tau fixed. I don't know, 0.05, and here is 0.09, for example. But if you took small enough, this is what gradient descent say, small enough, then you will converge. What is happening? If you start with this is okay for here, but this. So this is because of the curvature of the function. But here it's okay. But then this tau, the tau that you needed here was in fact 0.01. This is what you needed in this part. But you use this one. You can. It was a too large step. Okay. So it depends on the norm of the gradient also. This tau. So the thing is, it's better you use 0.01. I think we have some noise. Okay. So, yes. So this answers the question, I think, and also, so but someone could say, okay, let's start with 0.05, and then at the end put 0.01. There are strategies for this, for example, that at the end you make it smaller. However, a lot of cases you can just take very, very small one and do some accelerations and these kind of things. But it's important to know that one thing is this kind of behaviors, and the other thing is the oscillations. Oscillations is due to stochastic gradients. Okay. Okay, so in multi-classification is similar, but now y will not take any more 0 or 1. We'll take number 1, 2, or 3. So the values of y are not going to be continuous as in linear regression, but are going to be or 1 or 2 or 3. So discrete. So for example, here you have x1 and x2, and then you want to, and you know, this is not clustering, it's different from clustering. Okay, what you want, you know that all the points that are here are of some family. Number 2, the typical case is the iris flowers, that there are different families, and then this is a typical first example like machine learning, and then some of them are one family, another family, or another family. Okay, so you can have families and different examples. Okay. And one family you call it 1, the other one 2, and the other one 3. And more examples about this multiple classification. For example, is with x1, 2, is this a car? Is this a woman? Is this a cat? So being a cat is 1, 0, 0, or number 1. Being a woman is 2, and being a car is 3, for example, of an image. This is also multi-classification. You want to know, depending on x1 and x2, the output tells you the number. So for example, imagine you have x1 and x2, all the pixels. So 10, not 2 variables, 1000 variables. And the output is if this image is a woman or not. You know it. Someone tells you, you know. Sometimes when you in Google tells you if it's at a traffic light or this kind of thing, in fact, what you're doing is giving this level of a image. Okay. So this is kind of applications you can do, but you can do many. Imagine now, not 0 or 1, you extended the number of applications. Now, how we are going to classify? First wave 1 versus all. Okay, so we are going to have some theta's that will try to take some of them in one side, the green in the left hand side, and the red and blue in the right hand side of this line. So we will say that, and we will take a Heaviside function or a sigmoid function that if it's here, it's going to be 0, and if it's here, it's going to be 1. Okay. Is this blue data, or is it a car? So the same. Here will be 0, and here it will be 1, and the same for the third family. So now you see, we increase the number of theta's. We will need 1 theta for here, for this line. Now we need 3 lines. Another theta for here, another theta for here. Okay, so we increase the number of unknowns. Okay, so it's becoming more and more expensive. If you have identification of objects, that how many objects can it be? I don't know, or words. Imagine how many design variables you need. Okay, so it's the same idea, but now y is not anymore. It should be, instead of numbers, you can put it like this: 1, 0, 0. So if this is a car, 0, 1, 0, if this is a woman, and 0, 1, 0, 1, if this is a car. Okay, so now the data is like this. It's still 0 or 1, but it's vector. Its value is a vector. Typically, we put it in rows. Okay, so now before you have a vector of data, now each data, instead of being a scalar or 0 or 1, each data will be 3 numbers. So these 3 numbers, we will put it in rows. How is the cost? The cost is the same. You have 3 costs. You have the cost for this example, the cost for this example and the cost for this example. You have 3 costs and 3 thetas. Okay. So today we say that we are going to do for first time a neural network. But in fact, you have already did one yesterday, but we didn't call it like this. Okay, it was the first one, very easy one, with 1 layer, but not any internal layer, so just 1. Let's see why. But this is the good news, that you have already done one neural network. Of course, not very sophisticated, but the first one. Okay. So why we have done this? Why we call it neural network? These things, because it's a composition of what we call the neural model or logistic unit. We have to use a linear case. Remember, linear case with theta. Theta times x. X3 can be, but we can put here also, if we want, x1 squared. Remember. So here you put like a unit of the data, x0, x1, x3. And then here you put like the output. What is the output? Is the multiplication of theta times x. Remember, theta 0 times x0. This number is number 1, is the column ones you have put in the x. Theta 1 with x1, theta 2 with x2, theta 3 with x3. Okay? And then we pass this activation function or this sigmoid function that will give a number between 0 and 1. Here we will have 0 or 1. Here we have continuous numbers. Here also we have continuous numbers. We multiply this, we pass all, we sum all of them, we put it here, we pass the activation function, and we have a number between 0 and 1. This is what we call the logistic unit or neural model. So yesterday, I think you were doing precisely this. What this? How many thetas you had yesterday? 3 or 4? Depends, no, on D. So if you increase D yesterday, it's like you increase this column a lot with antithetas. Okay, so this is how you can see when you increase D, the direction D. So you did your first neural network, but just with no internal layers, just with the first layer and the output layer. Okay, questions about the neural logistic unit? Okay, it's clear, more or less. Here you have 2 things, important things that you have decided. First thing, what are you going to use here in the left-hand side? Which are your features? The second thing, that you are going to use linear theta. And the third thing, that you have to use a sigmoid function. There are other functions. ReLU, for example, is another example. Other kind of sigmoid functions, or functions, activation functions. Okay. More systematically, people use this image typically. I put it with this information just to see that here you just multiply and sum, and then here you pass the g, so you have h here, and then after h you pass g, and then you have 0 between 1 and 0. So these numbers are still between 0 and 1, and infinity, minus infinity, and infinity, and then after g you have between 0 and 1. Okay, but these two typically they go together in this g of h. Okay, just to see it more clear. What does it mean, 1 versus all, in the sense of neural networks? So it's the same, but now the output is not 1 or 0. We have 3 outputs because the output is a vector now. The output is 1, 0, 0, or 0, 1, 0, or 0, 0, 1. These are the typical outputs we have. Now, if it's a cat, it's like this. If it's a woman, it's like this. If it's a car, it's like this. The image. What are these values? These are the pixels, for example. Or this can be the coefficients of the Fourier transform of the images, or anything you imagine. but data. Now, theta, instead of being 1 theta, 2 and 3 thetas, sorry, 1 theta, you have 1, 2, and 3 thetas. 1 for each output. Okay. And these thetas, of course, should, once we pass the activation function, give between 0 and 1 and be very similar to y. So question, are these theta independent or related?
Within each other.
Between theta 1 and theta 2, for example.
It might be independent. They could be dependent, but if there are different clusters separated, they can be independent.
Yes, what do you think the rest? Theta 1, theta 2, and theta 3?
I would say independent.
Okay.
Honest, I'm not really sure.
So you have theta for here, and you want to solve the minimization of this error, all these errors. You will like to solve the minimization of all these errors, and also the minimization of all these errors. Okay, and these thetas will take care of these errors. This theta will take care of these errors, and this theta will take care of these errors. So this one, sorry, here, here, and here. But they are all of them in the same cost function. So some errors will be prioritized than others. Okay, let's see it. So now, what is the cost function? The cost function is j of theta is the cost, but now for each k, now you add another index, which is the index of the class. So y is not anymore a vector, sorry, a scalar, it's a vector. Okay. So now we have the addition of all these terms, but for each k. Okay. So all of them. I put theta in this color, but you have theta in all the other colors. Okay. So when you do the gradient, in fact, only the ones that are the first row depends on this theta. The second row depends on this theta, and the third row depends on this theta, and you add all of them, and you do it square. So when you do the derivative, you only have to take care of the ones that has theta, so this row. For the second derivative, this row, and for the third derivative, this row. Okay. So I think this is what we are going to do today. We're going to do a multi-classification example. We will extend the code, but instead of doing it for one output, we are going to have many outputs. Okay, and we will use also gradients, and we will use also gradients, and I think also today stochastic gradients. Okay, so now.
So at the end, the answer was that they are independent, but some of them might be more important than the others. Or
if you can minimize this, if you have theta 1, theta 2, theta 3, okay, then you minimize it between theta 0, only theta 2, and theta 3. So you can separate the minimization. Okay. So this classification, but as I was saying, one could say, once you see this, you say, so why should I do it like this? Why just not take all of them related? So here with here, then like this, Okay, so all of them are the thetas here. Okay, so now what you say is okay. Thetas will be all that can move from one to the other. Okay, but see, this was just two. So these two layers here, no, with no internal layers. Okay, but if you start putting more layers, okay, then you see how all the information is connected. It's like a network of connection. And it's called network because you have different nodes, you call it nodes, and relation of them, okay? And you could say that sometimes you would like to, some of them make it zero because it has no sense to mix things here with here or here that coming from the same thing. You would like to separate them. But you prefer to have like a connection of networks. And if when you optimize, some of them are zero, but then it's okay. It's going to be, you will have this decoupling. But you have everything together here. Data here comes here. So the data here comes here, but also here comes from these points, okay, independently. But these points comes from these ones and these ones from all of these ones, but this also from here and here. So you see that now everything is connected with neural networks, okay? Thetas, I forgot to say, but thetas are then you can see that's the intensity of these lines. When you solve the problem, you can plot it with colors if you want, and put it in white or transparent if it's zero, and black if it's very large. And then you can see the connections between the neurons, and you can see how everything is connected. Okay, so you can represent your solution. Of course, when you start having many layers, you cannot see anything. Okay, but just to see the intuition of what are these thetas. Okay. So this is an architecture, and this is very important because look, every time I pass to here to A1, so now A1 is going to be this G. So what do? I take the value, I multiply tan theta, then I add all the other thetas with X. Then I pass the activate the sigmoid. Okay, and I compute the numbers. These new values are between 0 and 1. Okay, here we add an extra one. You have seen that I didn't plot lines here to this one because this is the typical one column that you put. Okay, it's called sometimes bias parameter. Because here you also have it. This first one was the 1. Okay, so this does not depend on these ones. It's a column of ones. Okay. You see this that this is one or not? You remember that this is a ones. So if this is a 1, it never depends on the other ones. Okay, it's a number. So typically you can plot it like this, but sometimes you just plot everything together. And once you pass here, all of them are between 0 and 1. And now here you have a number 1, and then you multiply by thetas. Then you combine all of them. Then you add and you pass some sigmoids, and you add and you pass some sigmoids, and you have your solution, your data. And now this is something that you could say, or for me when I was studying it and seeing it, totally arbitrary. So first thing, why you connect everything with everything? Why you propose solutions with polynomials? Why with sigmoids? Why here you propose sigmoids? Why you want to be here between 0 and 1? You want to be between 0 and 1 here, but why here? And in fact, people are not using it. They are using other, not sigmoids and relus, for example. Right? So you can change the architecture. But now you have like a flexible way architecture to couple things. Not very much very general, but not adapted to any problem. And we will see that we will try to solve this way of computing functions, because this is a function, input and output. And you represent your function, the output is represented by this function, the input, with this connection, with this architecture. For example, in finite elements, functions are typically connected with nodes, which are displacements, and then polynomials. So these are the displacements will be these lines, the node values, and here you can have the polynomials. But what you will have? Linear representation. What will you have? A column, very, very long column, with all the polynomials, some of them local, so with local support. So for example, this could be the hat function of the corner of a domain. This can be the linear function or the shape function of the just in a side. So imagine a domain. I put these examples because I know that all of us do this kind of problems. So imagine a mesh. So you know you have shape functions that are in the nodes. So there are polynomials with local support. So every shape function will be something like this, depending on x. And then thetas will be the values of the nodes that you have to compute. This is a representation of a function with finite elements. It will be with one column, very large column, as many points as you want, with 0 intermediate layers. So, and this we have seen that is useful for computational mechanics. We have seen that we use finite elements for solving problems. And why? Because we know that it's somehow good to have local support, and polynomials was okay. So trying to solve computational mechanics problems with neural networks, this is what we will see Friday, and it is still controversial to see what is going to happen in the future. When I was in Oslo one month ago, and one of the plenary talks was about pins, which is what is going to be explained on Friday. And people are think that this kind of representation, it will be a good representation. And people that think that it's not going to be a good representation of a function, it's better to have a finite element, for example, discretization. Okay. There are some advantages and some disadvantages, and still we don't know where are we going. But this has been using for data and can be used just for representing a function. Okay. Another maybe inconvenience of this representation, the good part is that you can make it with a lot of levels of complexity. If you start adding many layers, it's the same thing I was explaining in lecture 2, the first day. Lecture 2. Of deep learning. Where is here? You see this example with a small information, you start doing features at each time more and more complicated, and at the end you have car, person, or animal. This is what we are doing now. But instead of images, we are taking numbers. For example, the features can be pixels or can be other things. And as you add many and many layers, you will have more and more complex things. So you can interpret and understand what is each neuron sometimes. Many times you cannot, or most of the times you cannot. Right? And it's this composition of functions. So you see your function, for example, for a PDE, you know, you has to be, when we do, for example, elasticity, when we solve elasticity, what do we do? We do linear combinations of polynomials with compact support. Linear combinations of shape functions with compact support. Now we will do a composed function, very composed, with a lot of theta, probably much more than what you need, but more complex, very nonlinear, very nonlinear. Okay. So of course this is very general, but that is useful or not for PDEs, it's another thing. Okay, so let's continue. Quick questions about this, more or less idea of neural network, how it works, how it more or less. Okay, and now you can start imagining how many configurations of networks you can have. You can have very small values here, A's. You can have many layers, a lot of columns, few columns here. What is the best architecture? It's also a parameter you can decide.
So, I have a question.
Yes.
You started with blue and apply, and then you obtain with the sigmoid then 1 or 0. But then you cannot apply the same function because you have changed your output is changed. So you need to use another function to go to the next layer.
You mean this one?
Yes. No, the full.
Yes, you see this one is not connected with this one. So it's a 1. So you will have a combination of values,
Yes.
with a 1 also. So you will need, it's a linear combination of parameters also, variables. And then, of course, all of them between 0 and 1. And then you will multiply by theta.
But the input is not 0.
Yes. The input is not, but the output it is in the sigmoid case.
Okay.
Yes. Then this A sees only ones or 0 between 0 and 1.
Okay.
And then here also, and then at the end you have between 0 and 1. But this is what I was saying, that no one asks that this one should be sigmoid, because this imposition of being here between 0 and 1, we don't need it. We need it at the end because we do classification. So you can use other kind of
No, I thought that when after the first level, you lose the information of what is.
You project it in a smaller space.
Okay.
With ReLU, for example, you don't have this. You don't do this change of coordinates and make it very small. Yes. Okay.
So it's always descending the space that you are, or can you stay in the same dimension?
Yes, it's a good question. I don't have a global answer for this. So you can have maybe something like this, and at the end, with some conversion, you have 3 outputs, for example. You can have something like this, but here you have to be careful. Why? Because you have only these features, depending on the data you have, you start adding a lot of variables. And maybe you can overfit. But then you also, if you add more layers, maybe you will overfit, but you can control regularizing. The answer is I don't know. Is it better to add more columns, or is it better to add few columns with a lot of rows? I think it's very dependent on your example and your problems. Of course, since you asked me this, I can explain that there is one interesting example that are called autoencoders, which is a neural network that what you want to do is that the input is equal to the output, but what you want to do is to pass all your information, and then has one layer that has few parameters. And then what you say is you can represent all your data with few parameters. So then it's like you compress here, because this is the data input and the data output, the same data. So you compress and you decompress. This is one special case that are used very much in compression of information, autoencoders. One thing that was changing a lot also was variation of autoencoders, which was precisely to ask to this small layer some properties. Okay, so the architecture, there is no an answer, a final answer or global answer for it. That's it. But it's the same as finite elements. Is it better? It's not the same. I mean, you can adapt more in one part. And is it better to have a lot of mesh there and a high order polynomial there? Or is it better to have linear and a very fine mesh everywhere? Or I have to have there very fine mesh and quadratic, and there linear, so you can adapt. So it's the same order of polynomials and also number of layers. So parameters that you can touch, how many and which is the order, how many layers and how they should be connected. So the architecture is something you design, and people knows sometimes how, depending on the problem. Okay, let's continue. Now, the cost function. So the cost function is the cost. I put j because sometimes I put j, but to continue with all our form, I will put f of 0. Remember, we have an unconstrained optimization problem. And then what we do is do composition of very simple neurons with theta, and then we compose all of them. Then at the end, we penalize if g is very close. If you want to y to be 1 or 0, sorry, and you get g equal to 0, you penalize a lot, and the contrary. We do the same procedure. Okay, and then you regularize with L2 norm in this case, for example. Why L2 norm? Because we have gradients. Okay. If not, you will have constraints, or you can use proximal algorithms, as I was saying. Okay. So now let's speak about forward propagation. That is probably a word that you will hear a lot of in neural networks. Forward propagation. And what is forward propagation? Forward propagation is a way of saying I'm going to compute the cost function. So let's see how it works. You give me x, then I will call it a0, a1. Then I multiply times theta, which is now it's a matrix. You see theta is a matrix. Then I got a value z. Remember this number, typically we call it h of theta x, is the hypothesis function. Then we pass the sigmoid, and then we compute new numbers, as you were saying, between 0 and 1 here. Then with this information I multiply by theta. I have the hypothesis function. Then I pass a sigmoid and I obtain this value here. Then again, I multiply times theta. I have this function, I pass the sigmoid, and then I have the output A4, which should be very similar to Y, which Y is the data of the output. Okay? Why is called forward propagation? Because in the network, you forward the information from the left to the right. You start here multiplying times theta, then you have A, you multiply times theta, then you have this A, you multiply times theta, and then you have the output here. So you forward the data from the left to the right. Okay. And this is called forward propagation. And today we will do it also. We will do forward propagation. Now, remember the gradient. Okay. Now, let's compute the gradient for this case. Now the gradient will be very, very difficult or more complex. Why? Because the cost function, which is the difference between these numbers with these numbers, will depend on here, which, okay, you just do the derivative. But if they depend on these of the deep values, you have to do chain rule of all to derive respect to this theta, or respect to this theta, or respect to this theta. So before we had one layer architecture. So what I recall it, how do we do it? We have the log, so the log gives you -1 divided by the value, and then the derivative of it has g prime, which is g1 minus g. And the derivative of h with respect to theta was x. Okay. And then the similar part, the second part was the log was 1 divided by the function times the derivative of the sigmoid function, which was the sigmoid function 1 minus the sigmoid function. So then we subtract the cancel this and this, and then we add them, and we have this formula here. Okay, this is what we had yesterday with one layer. Remember, this was very similar to regression, the gradient of the regression. Now, what's happening with several layers? So with several layers, you have to do it for the first layer. And if you do it for the first layer, of course, you will get the same thing as if you have one layer. Because you interpret this A as X. So you do the same procedure, -1, 1 minus the function, the derivative, you cancel this with this, the part that is Y, you do the derivative, you cancel this with this, you add this with this, and then you have this formula here. And then what you do is you call delta L to this difference. What is this difference? This is the error, in fact. The difference between G, so this with the output, how similar is what the numbers I have here with respect to the output, delta. Okay. And then you have the derivative of Z with respect to theta, which is X or A in this case. So now this it was a derivative, okay? Remember that A is the values of here. Before, instead of having A, this derivative was X. Why? Because we only have one layer. Okay? So this is why here, instead of having X, we have A of this line column. Okay? So the derivative of J with respect to L1 minus 1, so this theta, is the sum of this delta times A. And this is a pointwise product, where delta is the difference between G and Y. Let's do now L minus 2. A little tedious, but we have to do it at least once. The derivative of J with respect to theta is the derivative of delta L. So is delta L. With this, we have to derive the ZL with, instead of theta L minus 1, we have to derive derivative with respect to L minus 2. But zeta L is theta L minus 1 times L minus 1. So the values that are here inside are theta times A. Okay. So we put it here. The derivative of Z respect to delta L minus 1 is theta L minus 1, the derivative of A respect to L minus 2. Okay. And A minus 2, remember A is the solution of the activation function. So we have to do the derivative of this. The derivative of A is precisely G minus 1 minus G. As you see now, it's useful, or very useful, this property of the sigmoids. Now, instead of having G and 1 minus G, then you will have the derivative of A with respect to Z times the derivative of Z with respect to L minus 2. Okay, this is G and 1 minus G. And the derivative of L minus 1 divided L minus 2, or the derivative, is precisely this A, which was X here, or which was L minus 1 before. So now we have L minus 2 here, and we will call this delta L minus 1 to all of this, which is delta L tau L minus 1 G and 1 minus G. complex and tedious, I know, but this is what we have. They are deep networks, so we have to do deep derivatives. And we will call delta L minus 1. So the derivative of J with respect to L minus 2 is delta L minus 1 times L minus 2. 1 divided, where delta L minus 1 is delta L times all of this. And you see, now, G, you have already computed them. Because G are A's. Where were A's? We're here, in forward propagation. Okay. A's, you have already computed them. And you store it. So when you want to compute the cost, you store A's. And you store also Z. So for L minus 3 and this, it works similarly. Instead of having L minus 1 and L, you have L minus 2 and L minus 1, and you have an index less. Okay, you can do it by induction. So the thing is, you have a rule of multiplications, just of vectors, to compute the gradient with the cost, or that what you have to compute is these deltas. So how it works? Can you see it there? Okay. So deltas, you can imagine them also here in these rows, in this column, sorry. So if you want to do forward propagation, what you do is just multiply x and a and theta, and you compute sigmoids, and you store a's. Then this is forward propagation. If you want to compute the gradient, you have to take all the a's. So you go to the left, from the left to the right. You have all the a's. Then with these a's, the last one, you subtract y. Then you have your first delta. With this delta, you multiply times theta, so times this one. And then you have the new delta that multiplies g prime, which is g. 1 minus g, which in fact is a. G is a. So you have delta here, you multiply times theta, then you multiply point y times a. Not only a 1 minus a. And then again, with this delta, you multiply times theta, and then you multiply times a 1 minus a. Okay. This multiplication is pointwise. So the thing is that in fact, what we have is, I think here I have a mistake. This is a 1 minus a also. Not sure. We have to look at it. But this is called backward propagation. Why? Because first you go from the left to the right, you do forward propagation, and then you compute from the right to the left, backward propagation, to know all the gradients. So from the left to the right is to know the cost, from the right to the left is to know the gradient. But in fact, knowing the cost is okay, but what you want is the gradient. So to do the gradient, you need always to go from the left to the right first, and then from the right to the left, and then you compute the whole gradient. Okay. Questions about forward and backward propagation?
I have a question. Because to compute the backward propagation, you need all the A's. So you said before that calculating the cost might be very expensive. So this, even if you do a stochastic gradient, you need all the A's of the layers before, isn't it?
You can do it with a stochastic with just one of them. Some of them. You see here, maybe it's not clear, but here, this is the features. But the other thing is the data, how many? So how many data you have? So how many times it will pass from here to here? Yes, I think I should comment this. So one thing is the features, and the other how much data we have. So probably this vector will be in the left, I don't know, 1,000 times. So I will have to do this multiplication 1,000 times and one multiplication this 1,000 times. So instead of doing this for all of them, you just do it for hundreds of them. But yes, you're right. And this is a little 90s styles or 2000 maybe, but it has changed a lot. So this was famous neural networks with sigmoids in the 95 or yes, 2000, because you have these properties of the cost, of the derivative, and also these properties of stochastic gradient, multiplications. You take a lot of profit of this, but at some point, this was one disadvantage. At some point, you couldn't have more and more unknowns because you didn't have this computational capacity and GPUs and this. Just to tell you, yes, people in machine learning, a lot of them, they work with GPUs. Not so much. They are also working on parallel computing, of course. But with GPUs, it's very important because you don't do inverses, you do matrix vector multiplications, and in your own computer can have fast solutions. Okay. They rely so much on that. What else? Yes. About this is that was famous, okay? But it was famous with sigmoids, and also we were using sigmoids, and we were using this network. So the question is, what is happening if we have other activation functions? Do we have this property? Do we have this forward and backward propagation? Okay. Could we really have the same properties and speed? So now what people is using is automatic differentiation. So what you do is, instead of computing as I have been doing here by hand, you can do it, and we have the formula. Today we will use the explicit gradient. I think we are not going to use automatic differentiation. No, but you can have also automatic differentiation gradients. Okay, then you just compute the loss function, the cost, and with this you propose your architecture, and then the gradient is automatically. And this is very useful because you can propose different architectures. You can propose many. Now I can change the activation function. I can change the architecture. I can change the basis. Instead of positive having cosinus, I will put exponential. Okay, so and these things has changed a lot. I would say that automatic differentiation has impacted a lot machine learning community. So this is important, of course. On Friday in pins, you will be using the TensorFlow, and there is automatic differentiation, and I think that there are a lot of tools, and this is a very good point of machine learning, that there are tools where you have automatic differentiation and you can take profit out of this. So this is nowadays what people do. Okay. Okay. So what else? We propagate the error. Okay, with backward propagation, and because we go from the right to the left. Okay. And then we use a stochastic gradient. Okay. Also, we can use regularization. Okay. We have to use a regularization, different kind of regularization. As I was saying, we can use the L2 norm, but other possibilities are also possible. Right? Okay. Just to conclude, this is neural network for classification. Questions? If not, because I want to pass to another thing of neural networks.
Just quick question about what you were talking about, the architecture that is fixed. I don't know if you have explored the possibility of using automated machine learning, in particular architecture search, something like this, I think it's called. Because I don't know how useful or how profitable it can be, because training the network will be expensive. And on top of that, changing the parameters, I don't know if online will be more expensive, and changing the topology, changing the hyperparameters. I don't know if you have explored this.
No, I don't know, and I have no intuition of what would be the best, honestly. I don't know if it's better to have more layers or larger layers, or deactivate these, or I don't have an answer, because it's somehow philosophical also, because what is better, and it's very problem dependent, I would say. What is better for this problem? What do you want to solve? What kind of function you want to represent? And yes, people are trying to learn also the architecture. And this is another hyperparameter you can have. But I don't have an answer of it, honestly, to know what kind of architecture we should explore. I don't know. But I think there is room for this, of course, to think of it. My impression, or my point of view, is that the architecture is important, but the representation learning, I would expand, or I think is very, very important. What you put in the left, what you put here, and if you can have other representations of your data, than just putting sigmoids that you, or other functions, activated functions. So, and I think that's what have been changing a lot, this idea of changing the representation of your data, not only the architecture. This idea of architecture was, we had it before, but now deep learning and understanding representation learning, this is what I think will help more. But of course, learning the architecture is also something we could do. Yes, and I don't know which way we should go. Okay, more questions? Okay, so just to finish this part, okay, of classification, there is another example. Support vector machines. It's also classic now, the machine learning community, probably would call it. And support vector machines are other way of classifying. What you want to do is you want to classify two different data, this in one side and this in another side. Okay. What you do typically is you say, okay, I will pass a line, a vectors. I plot it in 2D, but the idea of this is that you do it for any dimension. What you try to do is you pass an hyperplane, or you try to find an hyperplane that better separates by the data. So imagine you have a line, and theta is your normal of this line, the normal. I put here omega, but I mean theta. Okay. So if you change the value of this line, you will move it with the same theta. You will move it to the left, or you will move it to the right. Okay. You put number 1, you go here. You put number 0, you go here. You put number -1, you go here. And for the same theta 0. So what you say is, okay, if the data is separable, if I had a space for putting a line, and all of them will be in one side and the other one will be in another side, when the data is going to be 1, I ask to have theta x minus theta 0 larger than 1, so all here. So when we have data that is 1, then I will ask the values that theta I have to find when I multiply times x are going to be larger than 1. And the contrary, see that here, when in supervised machines, you don't have 1 and 0, you have 1 and minus 1. So the ones that were called 0, now you put it a minus 1 in the level. Okay. So now, if you want to be minus 1, you ask that theta and theta 0 in these points are such that when you multiply times x, they are going to have value less than 1, a minus 1. You see more or less the interpretation or not? I'll say it again. So you have data here in the left, you have data here in the right, and then here data with y equal to 1 and y equal to minus 1. You know that if this hyperplane, you can change it with just this parameter 1, 0, and minus 1. Okay, so what you say is here, when I multiply times x1 and x2, times theta, then and I subtract this theta 0, both these numbers, I have to compute them. I have to find the best ones. These are thetas, always. Then I will be larger than 1 for this point. I want to impose this. This is what I want to impose, to find thetas such that when I multiply times x, these points that has some x, then all of them will give you a value larger than 1. And when I multiply this value that has some x, when I multiply by these thetas, all of them has values larger than minus 1, smaller than minus 1. Okay? This is the conditions you want to impose. This is how you see the problem. How you do it? So you can see that if you multiply 1 and minus 1 times this is data, then you have the same constraint for all the points. Okay? So these two constraints can be put in one constraint, just multiplied by this. Now, you can compute, this is the normal, and you can do the distance between this and this, you can subtract, and you can see that this is the norm of theta 2 times, because from here to here it's twice. You subtract this minus this, and this is in fact 2 divided by the norm of theta. Okay, you can compute it. So what you want is to separate them the most, these two data. You want to find a hyperplane or theta such that when I took 1 and minus 1, I separate the most the data. Okay, this is what the objective, such that I fulfill the constraint that here I will have 1, and I fulfill the constraint that here I will fulfill minus 1. Okay. Now, sorry, because I had to change the notation to adapt for this course. And then this is not theta, it's theta and theta 0. Okay? Okay, this problem. Is this problem convex? What would you do to solve this problem? For example, this one. Okay, this problem is a constraint or a constraint optimization problem? Constraint optimization. What are the optimality conditions for constraint optimization? KKT. What algorithms do we have for KKT or constraint optimization? This morning. Lagrange, interior point methods. Okay, for example, there are more, of course, but we can use both. The thing is, you can change this maximum with this minimum. So 1 divided by theta is the same as maximizing this, is the same as minimizing this. And this problem is better well posed than this problem for sure. Why? Because this is hyperbola and this is quadratic. this happens so much in optimization that you have a problem that is difficult. You change the cost, but the solution is the same, and you want to solve. You want to find theta, then you can compute this if you want, but you do a trick in order to change your cost and put it in a way that you can solve it fast. This happens many times. So here you have 1 over theta, and then you have theta here. Now, this problem is theta squared. Does it remind you something, theta squared? Or we have seen theta squared? Theta squared, L2 regularization. Exactly. Okay. So it comes here also again. Okay. But now we have a constraint. What can we do with the constraint? An equality constraint. What have we seen this morning with inequality constraint? How we can pass from inequality constraint to unconstrained optimization problem?
Interior point.
Interior point method, exactly. So with interior point method, we have two things. We have one term is the cost, and the other one is the constraint. So the central path will be this, and the constraint will be this. In this example, you can interpret it as this being in the central path, and this one, the regularization, as we have seen many times, is the cost function in this case. Okay, but both are in the cost. Okay, thanks. So what I was saying, yes, if you want to maximize this, better you use this. If you want to, imagine you have the log or something or exponential, if you know it's monotonic, better use a quadratic because it's better will pose the problem. You can rechange many times your problem. Okay. This, which is positive, we usually write it in the canonical form, so we make it negative. Okay. Why? Because we like to write it like this. Okay. And now, sometimes you can relax the problem also, and you add some, but you can solve that problem there. But the thing is, not always happens that the problem is separable. Not always you can find theta such that all the points in the left are going to be larger than 1, and all the points in the right will be -1. Usually, you don't find this. So you adding this constraint, inequality constraint, that what I was saying before, that the way of putting an inequality, we can see it as an indicator function, so infinity, if you are not a feasible point. So maybe you cannot find any feasible point, and the solution is infinity. You don't have solution because there is no theta that is able to separate between these two data. Okay, so and it happens. Of course, the normal thing is that it happens. So you relaxation again the problem, or you can regularize it. You can see it as you prefer. How? What you can do is to add an extra variable. Okay, auxiliary variable, also called chi, where you say, okay, I want to be larger than 1, but not always larger. Just I will leave the capacity of not being larger than 1, but maybe being larger than, I don't know, 0.9 or 0.6. You relax it. If chi is 0, you have the same problem. But usually chi is not 0. You will find solutions with other values of chi. And you relax it. Now, ways of relaxing it. First thing, you put it in the cost. But you can do it in a, you can add many as all the constraints you have, but it appears a Lagrange multiplier. but you can add it in many different forms. You can add it with L1, with L2, with L infinity. Maybe what you can add, as we were seeing in the first part, that you can ask just one chi and one vector of ones, only one variable. You will relax less. You will be more, you will ask more than the other case. Okay, so you can relax in different ways. But this problem is solvable. You can solve it. Okay, and you will of course separate, but some points this chi will be larger. Okay? And then you can formulate your problem, your primal, relax, with a dual. Okay, and I don't have time for this in the sense that I will have to do all the derivations, but you remember what we have to do to pass from the primal to the dual. What do we have to do to pass from the primal to the dual? Who remembers? What do we do?
First to write the Lagrangian.
Lagrangian.
Take the infimum with respect to theta.
To theta. Exactly. And then we get the dual. And then with the dual, we maximize. That's what we do here. Let's have a look to lecture 1. No, this was lecture 3. And we have plot express. I prepared this example explain because I knew that I had to explain super vector machine. So it tells me that then this primal, you can write it as a max of a dual problem. Okay, we have done a quadratic with linear equations, but now we don't have this example. It's more complicated to show it. Okay, you can do it, but you do the same procedure. You have the Lagrangian, you do the infimum, then you find the theta, you plug it inside, and then you get this. Or in linear programming, which is not the case, but in this case, but yes, this is linear programming, I think. This is linear programming, yes. No, quadratic, sorry, quadratic programming. Okay. So it's not this example, it's a combination of this with this. We didn't do this example, but you have to do the same. You have to take the infimum of the Lagrangian, then you take the Lagrangian, you obtain the better theta, and then you plug it inside, and you have everything in terms of mu. So at the end, one problem with inequalities becomes also inequalities, and the constraint, these constraints go here, and B, what was here, what is now in the cost. Okay, so the primal, you can solve it, but also you can solve the dual. And usually people that are solving support vector machines, they solve the dual, okay, because it's quadratic. And with this, you have very fast algorithms, which, for example, interior point methods. Right? In this case, with the interior point method, you will solve this dual very, very fast. Okay? But as I was saying, you cannot have many data. Nowadays, support vector machine is not as much using as neural networks. Okay, but there is another thing that people, and with this, I try to finish. What they do is they change the representation of X here. Remember, X was the data. So here can be quadratic, cubic, and they do it. They transform this with one thing that is called the kernel trick. That you represented this data instead of like this. You do a change of variables. You do this. You see it as a kernel, and you change the kernel, the way of representing the data, and then you solve the same problem, but with more information about chi, x1 and x2. So you change the way of representing x with a kernel that can penalize one thing and not others, or to be in interior. There is now an absolute kernel of what do we have to do. So in support vector machines and also in other cases, you can just change the prima to the dual. You represent your data, and you can use some kernels. And here you can use interior point method, for example. Okay, so this is an example of support vector machine. We are not going to code because we don't have infinite time. We will code just neural networks, We will do stochastic gradient, and we will code forward and backward propagation. So let me do a wrap up of what we have done today. We have seen classification. So yesterday we just seen 0 and 1. Today we have learned how to do with 1, 2, and 3. We have seen that the cost is different, that we have to pass 3 lines, and theta's are independent. We have seen that, in fact, yesterday we were already doing our neural network, but with just 1 layer. We have seen another more systematic way of presenting the neural unit. We are solving the one versus all problem, so they are independent, and what we want to do is to make this similar. Now, why it's a vector? It's not anymore. So we put it like in columns and data in vectors. So here 0, 1, 0. We didn't put it as 0, 1, 0, 0, 0, 1, for example, any data. Okay. Theta, it's a matrix, but of course, when you code it, you will have to give it as a vector. Remember, codes, you have to reshape this.
Another question.
Yes.
Just right there.
In neural networks and constraint system, there exist multiple combinations of weights that can minimize the loss. Yes, or under constraint, over constraint is applicable to the linear system. I think we are mixing things here. So one thing is constraint optimization problem, and the other thing is unconstrained. So the answer is, in terms of optimization, it's unconstrained optimization. In terms of over constraining or overfitting and underfitting, maybe I think this more comes the question. It depends again on how large is your network, how many layers you have, and how many data you have. So if you have a lot of data, maybe you can have many thetas, many layers, but you can also try to, you can have overfitting, but then you regularize, and then you can have the proper lambda per parameter that fits well your data. Okay. So the neural network is, as you see, an architecture of units that are all of them combined. The cost function has the same representation, but now just with K, with now more data. We have seen forward propagation, which is going from the left to the right, computing A's. We have seen how was the gradient yesterday, but how is the gradient today? And now we have to compute these deltas all the time. So if we do so, we have done this for our activation functions. We have this rule of deltas. So now, if you want to compute the gradient, we have to go from the left to compute it A's, and then to the right to compute it A's, to the left to compute it delta. So forward propagation and then backward propagation. Very important. Now we use automatic differentiation, and we can use different kind of units. And then we have also to regularize. And finally, we have seen another example of classification, which is support vector machine, that is difficult to separate. We see it comes with an inequality, so it's a constraint optimization problem. In this case, constraint optimization problem. So this example, you will solve it. The primal, you can solve it directly when you relax it, because maybe you don't have solutions. You relax it, you have solutions, you use an interior point method, or you just solve the dual and you change the way of representing data. Okay. And for this, you will use interior point methods, for example. And this is an example of machine learning that is with constraint optimization. That is what we have seen this morning. Okay. So now, this afternoon, we will do the practice for neural network and classification, backward propagation and forward propagation. Okay, with regularization, stochastic gradient, and we will try to internalize all of this. And tomorrow, I will explain as part of a statistical learning, so how to see all of this more in the statistics ways, so more Bayesian and relative view of the data. Also, what means negative log likelihood? What is the likelihood? What is the prior? What is the posterior? These are topics that came always in machine learning. And then I will explain unsupervised learning, which we will have a PCA, we will have CIMNE, and we will code it also on Thursday. On Friday, we will have constraint optimization, where the constraint will be a PDE that instead of trying to solve the constraint optimization problem or the optimal PDE constraint optimization problem, we're going to solve it with neural networks instead of the chain method. Okay. So I think it's time for break lunch, and we see you in 14:30.
Or I can see 100 days.